Good afternoon, ladies and gentlemen.
Yep, here we are, 25,000 feet cruising above the clouds. Today we're going to talk about cruise performance, specifically what it is and how you evaluate it. But before we jump in and start pumping out those old equations, what's something you consider or even think about when you want to take a trip with the family?
Are we there yet? Gotta go to the bathroom.
Oh, not that. You measure your car's cruise performance by measuring its gas mileage.
Well, we use the same idea to evaluate an aircraft's performance, only instead of miles per gallon, the aircraft uses miles per pound of fuel. The goal for a good aircraft design is to get the best mileage possible, just like in your car. Another thing we can do in airplanes is fly as long as possible. Here we're less concerned about mileage and more interested in maximizing how long the planes can stay airborne. This is called the plane's endurance.
Well, that's basically what cruise performance is. But now in order to evaluate cruise performance, now we got to start looking at the equations. Fortunately, you've seen most of them before.
Recall from earlier sessions, in level unaccelerated flight, or just plain cruising, lift equals weight and thrust equals drag. Rearranging the lift and drag equations to solve for the coefficient of lift and the coefficient of drag, we get CL is equal to 2W over rho v squared s, and CD is equal to 2T divided by rho v squared s.
You see, the terms that are common to both equations are the velocity, the density, and the wing area. If I say at the same altitude and don't change the flap setting, then the density and the wing area stay the same.
All we're left with is the velocity, the weight, and the thrust. Ideally, the best endurance comes at an airspeed where we get the most lift for the least amount of drag. To determine what the optimum speed is, we develop a ratio between the lift and drag. During a test flight, if I measure the weight and thrust at different airspeeds, I can use this directly to calculate the CL and CD. Making a graph of CL versus CD, the plot has a shape of a parabola. This curve is given the name drag polar. We'll call it drag curve for now. Now if I draw a straight line from the origin to a point where the line just touches the drag curve, this is the tangent, I get the point where the CL divided by CD ratio is the maximum, or the optimum CL for maximum endurance.
Again, this means I have the most amount of lift for the least amount of drag. And since drag determines how much thrust we need, and thrust determines how much fuel I'm going to use, I get the most amount of lift for the least amount of fuel.
Rearranging the lift equation to solve for velocity and putting in this value of optimum CL for maximum endurance, I can determine the optimum endurance speed. Okay, let's try this and see how well it works.
So, we're currently at 7,000 feet, 115 miles an hour, and according to the engineers, this is the 115 miles an hour gives us our best endurance and the lowest fuel flow, or the lowest number of pounds of fuel per hour. So if you look at our fuel gauges here, we got 7.4 pounds per hour, or correction, gallons per hour on the left, and 8.6 gallons per hour on the right. And I'm at 115 miles an hour. If I slow to 105 miles an hour, I'll bring the throttles back a little bit initially to get slowed down. Okay, there's 105 miles an hour. And you can see at the left engine I'm burning 8.1 gallons an hour, and on the right engine I'm burning 9.5 gallons an hour. So that has increased my fuel flow. That means that flying slower, I need to add more power to fly slower, so that means more fuel. Now let's go a little faster, so I'll even put more power in and just slightly nose over to get back down to 7,000 feet for us here. We'll go to 125 miles an hour and maintain that speed. And we'll see what the fuel flow does then. Okay, there's about 125 miles an hour. We'll level back off here. Get that zeroed, and this is about 7,000 feet. It's a little turbulent today, which may have an effect on it. Okay, 125 miles an hour at 7,000 feet for level flight. I'm burning 8.1 gallons an hour on the left engine and 9.5 gallons an hour on the right engine. So you can see, and we'll verify back again at 115 miles an hour, that our best cruise airspeed for the lowest fuel consumption or the highest lift to drag ratio is at 115 miles an hour. Let me slow back down here a little bit. Okay, there's our 115 miles an hour again. As you can see on the left engine, I got 6.2. On the right one, I've got a little bit more power carrying. I'll see if I can balance them out here a little bit better. There we go, all trimmed up, 7,000 feet, 7,080 feet, level flight, 115 miles an hour. I got 7 gallons, 6.9 gallons an hour on the left engine, 9.2 gallons an hour on the right engine. So anything faster or slower than our best lift-to-drag ratio airspeed is going to use more fuel. So there we have it. We kind of proved what we were talking about. Any questions? You can see that although the fuel only changed a couple gallon to 2 gallons an hour difference off the optimum cruise airspeed, for us over the course of a 3-hour flight, at 2 hours or 2 gallons an hour per engine, that's 6 gallons an hour per engine, or another whole hour's worth of flying time. And that's not bad for us, but think about a 747 that comes off its optimum cruise speed, and I'll tell you what, he's burning thousands of gallons an hour difference, and that makes a whole lot of difference in how far he can go.
Obviously, the weight will change as the fuel is burned. So looking at the equations again, we can see that as the weight decreases, the lift required decreases. Therefore, the airspeed for optimum CL is lower. In order to stay airborne as long as possible, that is, get the maximum endurance, I should fly slower. This is the procedure the airlines use when they get stuck in a holding pattern waiting to land. However, when you're traveling cross-country, instead of maximizing endurance, we would maximize the range, or how far we can travel on a given amount of fuel. The optimum value of CL for best range ends up being about 70% of the optimum value of CL for best endurance. Regardless of whether you're flying best endurance or best range, as fuel is burned and the aircraft gets lighter, we should decrease the airspeed. But we don't fly to go slower. We use airplanes because they get us to our destination faster.
As the weight goes down, and we want to keep the speed high, and still fly at the optimum CL, what can we change? Well, about all that's left to change is the density. And I can change that by climbing to a different altitude. So what I'll do is I'll cruise at one altitude for a while, say about an hour or so, climb a couple thousand feet, cruise there for an hour or so, and continue this step climb throughout the entire profile until it's time for me to start my descent.
This holds true for propeller-driven aircraft also, except the amount of fuel burned during the course of a flight is much less than a jet, so the weight change is less. For this reason, most prop-driven aircraft usually start at the maximum range airspeed for a specific altitude and stay at that airspeed for the entire flight. The price they pay in cruise performance is small.
Speaking of cruise performance, now that we've figured out how to calculate the best cruise performance, all that's left is to get back on the ground. So next time we'll look at landing. See you then.
Is there anything else I can get for you, sir?
Oh no, those peanuts filled me up so much I couldn't possibly eat another thing.
Okay, great.